All right, so the goal here is to understand something called Rolle's theorem. R-O-L-E-S. So this is Rolle's theorem. And Rolle's theorem is really a special case of something a little bit more general. Now your challenge here is to draw a function that's equal on the endpoints of some interval. It's continuous on this interval and differentiable on this interval. So it doesn't really exactly matter what you drew. Could look something like that. Maybe some of you drew more of a U shape down here. But one thing that has to be common to all your graphs is that at some point, say here or here, you have a tangent line which is horizontal. That's the conclusion from Rolle's theorem, is that someplace in here, f prime of x has to be 0. So then, for some value c in the interval a to b, f prime of c equals 0. That's the conclusion with Rolle's theorem. And that's nice. Rolle's theorem came first, and then it became general. So it was generalized. So let's take a look at an example of Rolle's theorem. And you can follow along with the links on D2L. So let's take a look at example A. So example A, we've got f of x is 3x squared minus 6x plus 4 on the interval -1 to 3. So, okay, let's check that out. I think I've got that one already up. So here's our function, and let's look at it on the interval -1 to 3. So -1 there and 3 there, we're good. So notice that the endpoint, the function at the endpoints are equal. So I guess I do need that here. F of -1 and f of 3 are both equal to 12. So okay. Now the parabola here is nice and smooth, continuous and differentiable everywhere, so we got that satisfied. And what the Rolle's theorem guarantees us is that there's some point in between where the slope of the tangent line is 0. So right down here, that's where the tangent line is 0. That's what Rolle's theorem is guaranteeing us to be able to find. So the problem asks you though to find all values of x that satisfy Rolle's theorem. So that's this right here. Let's see if we can't do that algebraically rather than just working with Desmos. So first thing we need to do is calculate f prime of x. That's going to be 6x minus 6 and set that equal to 0. So at x equal 1 is the point that satisfies Rolle's theorem. All right, a nice result. It's not the result that we're really going to make the most use out of, but it is the result that gets us the next thing that we want, which is the mean value theorem. So let's look at the mean value theorem and see if we can't make some heads or tails out of the mean value theorem. So let's see. Here we go. So let's talk about the mean value theorem. The mean value theorem is really just generalizing this. What we're going to do is we're going to get rid of the requirement that f of a equals f of b. They no longer have to be equal at the endpoints. So here's the requirements for the mean value theorem. We need to have a continuous differentiable function on AB. And if that's the case, then at some point, the slope of the tangent line is going to equal the slope of the secant line. So here's your slope of the secant line. And if we plug in some points, it would look like this. A and f of A, B and f of B. If you just treat this like regular set of points, then we can find the slope of a line in between these. It's going to be your x1, y1, x2, y2, y2 minus y1 over x2 minus x1. That's the slope of your secant line. What tells you the slope of the tangent line? The derivative. I'm not sure it shows up there very well, but that's f prime of c. At some point in this interval, if you have a smooth continuous function, then the slope of the secant line and the slope of the tangent line have to be equal. Now your first glance at this might be to say, well, okay, big deal. But it actually is a big deal because this is going to give us a nice concrete footing for what we've said all along. What do we know about a function when the derivative is positive? What's telling us when we have a positive derivative at some point for a function?
Slope is positive?
Yeah, the slope is positive. It's increasing. And this gives us kind of a nice concrete way to say that. If you have an increasing function, then that means when you move from left to right, that you're moving up on the y-axis. And when we do f of b minus f of a, you're going to get a positive number. Now, if that's positive, b minus a is always going to be positive. So this ratio is positive exactly when the derivative is positive. In other words, if the first derivative is greater than 0 on some interval, then the function's increasing on that interval. That's kind of nice. That's actually really nice. What about if the first derivative is negative? Well, the first derivative is negative, then the function's decreasing on that interval. And if y prime equals 0, then we have either a maximum or a minimum point. So, wow, okay, great. Let's keep going with some of our work in the problem sets. So let's move on to example B here. And there's links here that we can look at. So let me pull that one up. Here's example B. Actually, no, that's not example B. All right, let's just change it. That looks like it was example A. So I want x cubed minus 3x plus 4, and I want that on the interval -2 to 2. 2 less than or equal to x less than or equal to 2. All right. All right, so there we go. So at -2, we're at 2, and at +2, we're at 6. All right, so a nice continuous function. Let's take a look at this relative to the mean value theorem. First of all, is this a continuous function on that interval? Is our function continuous? Yeah, polynomials are always continuous, so that's kind of a nice thing about polynomials. We're going to take advantage of that in Calc 2. Let's see. Is it differentiable everywhere? What kind of points would we be worried about? What do we have to look out for? Vertical tangents, discontinuous, and corner points, right? So those three types of points are places where the derivative would fail to exist, but none of those is going to be the case with a polynomial, so we're good there. Basically, this satisfies the mean value theorem. Now, it doesn't necessarily have to be differentiable on the endpoints, but it is, so we're good there. We'll see if we can't find the point that satisfies the mean value theorem for example B. So let me do that work over here. So actually I'll do it down here. F of x is x cubed minus 3x plus 4. X, f of x, negative 2 and 2. Let's see, f of negative 2 was what? Was it 4? Or is it negative 2? Let's see, let me go back here. That was 2. All right, so let's figure out the slope of the secant line first. M sub secant would be 6 minus 2 over 2 minus negative 2, which would give you 4 over 4 or 1. So on average, the function is increasing with a slope of 1. That's the average rate of increase. What the mean value theorem tells us is that someplace in between negative 2 and 2, we should find a place where the derivative is equal to 1. So let's see if we can't find that. So let's see, we're going to set 1 equal to f prime of x. I mean, technically, if you want, you can put an f prime of c, but what's f prime going to be for us in this case?
3x squared.
3x squared minus 3. Cool. So, all right, let's see here. As far as solving this is concerned, I would move the 3 to the other side and get this. 3x squared equals 4. 4 thirds equals x squared. How am I going to solve for x? Square root. Except there's something wrong. Ah, thank you, sir. Need that plus or minus. Now, if you want to play with it some more, you can. You can say, oh, all right, well, let's see. That's going to be plus or minus 2 over the square root of 3, or better yet, plus or minus 2 square roots of 3 over 3. I'm not going to be really worried about this. I mean, if you got down here, my inner child would be doing somersaults. I'd be very, very happy. Do I need both the plus or minus? Yes. Now, what you have to look out for is that sometimes one or other of these points might not be in your interval. But both of these points are going to be inside the interval negative 2 to 2. So we're in good shape. The 2 points that satisfy the mean value theorem here are going to be both of these, plus or minus 2 square roots of 3 over 3. Let's see. Let's demonstrate that. So one of the cool things about Desmos is you can do this. You can graph, say, the derivative, y equals z prime of x. And what I want to know is what's the slope of the tangent line at those points. So I can ask Desmos to calculate z prime of, let's do it as a square root of 4 over 3. Oh, and it exactly equals 1. No surprise there. If I put in a negative, it's still going to equal 1. So at both points, the slope of the tangent line is exactly what we said it would be. All right, how are we looking on example B? Okay, thumbs up. One of the biggest things we get out of the mean value theorem is what I started out with here, and that is that the function's increasing when the derivative is positive, it's decreasing when it's negative. We're going to continue to work with that. But let's work on example C next. Example C, we're going to dive back into Rolle's theorem here. So let's look at that. verify that the function satisfies the three hypotheses of Rolle's theorem. Now, if you're following along on Desmos, I chopped off the function there just so it wouldn't be too busy, and it's a little easier to see here. We can see the endpoints of the interval from pi over 2 to 3 pi over 2, that the function is equal, or the value of the function at these endpoints is equal. So we're good there. Is the function continuous? Yeah. Now your quick check for continuous is, can you draw this without lifting your pen from the paper? There's no jump discontinuities, there's no holes, there's no, let's see, there's no vertical asymptotes in this graph, so we're okay there. It's continuous. So let's see, f of pi over 2 equals f of 3 pi over 2. So that one's checks. It's continuous and it's differentiable. So all three of those check. Let's see if we can't find the point that's guaranteed by the mean value theorem. So that would mean finding a derivative here. Don't think I'm going to try and cram that in here. Let me go to a new sheet. So example C. F of x was sine of x over 2. Now for our convenience, let me rewrite that. Let me rewrite that as sine of 1/2 x. Just to make it clear that we really don't need to use the quotient rule here when we differentiate this. Do I have to use the chain rule? Yeah. Because you have an inside function. What's the outside function? Sine. Good. So f prime of x is going to be the derivative of the outside, which is cosine of 1/2 x times the derivative of the inside. 1/2. Thank you. Derivative of 1/2 x is just 1/2. Now at some point, that's going to equal 0. And we want to solve for that point. So, okay. Let's see. What I would do if this was my problem is I would multiply both sides by 2 and get rid of that constant of 1/2. So multiply by 2. That's going to be cosine of 1/2 x equals 0. And then what? Well, we could take the inverse cosine on both sides. Try and get rid of the cosine on the left-hand side. So cosine -1, cosine -1. On the left-hand side, I get some nice cancellation. Cosine inverse and the cosine cancel. On the right-hand side, I need to know at what point I've got an angle whose cosine is 0. Where is that going to happen?
Pi, 2 pi.
Cosine is which coordinate on the unit circle? So it's the x coordinate. Let's draw ourselves a nice little unit circle here.
Pi over 2.
Yeah, there you go. Here and here. So the two places where this is going to equal 0 on the unit circle are going to be at pi over 2, 0, 1, and 0, -1. So pi over 2 and 3 pi over 2. Now I don't think we need to solve this in all its possible generality. Pi over 2 or 3 pi over 2. Those should be good enough. But we still haven't solved for x. What do I have to do to solve for x? Yeah, thank you. Multiply by 2. So let's multiply both sides by 2. So if I multiply both sides by 2, I get x equals pi or 3 pi. How come I can ignore 3 pi? Yeah, it's not in our interval. So really the only answer that we get out of this is pi. I mean, not a big surprise. You can kind of look at the graph and just see that it looks like, oh yeah, x equal pi, that looks like about the spot where it's going to work. So right here, at pi, that's where you're going to have your horizontal tangent, is right there. So a lot of the reason for this was just to give you some practice working with trigonometric equations, remind you on how to do that kind of stuff. I mean, the overall conclusion is not a big surprise. Comments or thoughts on that one? Let's continue. Let's move on to example D. So here's a function that looks like something that came right off your last test. F of x is x plus 5 over x. And let's see, we're going to work with this in the interval 1 to 10. First of all, see if it satisfies the mean value theorem. So satisfy mean value theorem. Let's find out. So let me shut off these graphs and move down to example D. So, okay. We're going to look at this on the interval from 1 to 10. So let me do this. 1 less than or equal to x less than or equal to 10. Do I have a nice smooth continuous function at that on this interval? Is it different? No, it's not. Isaiah?
Yeah, there's like a dot like right next to it too.
Oh, that's just it's minimum point. It's not.
Oh.
It's not a hollow point. Thanks for asking though. Yeah, but it's not undefined anywhere. So I think we're okay on that regard. Let's put in the endpoints here. Let me make those a little bit more colorful here. So there you go. There's our endpoints. So yeah, it is a smooth, continuous, differentiable function on the interval 1 to 10. So we're okay there. So let's move on to the next step then. Next step is to find the value of the function at a couple points. And to this end, on the graphing calculator, you can make yourself a little t-table. Do we need to review that? Are you good using the t-tables on your graphing calculator, or do you want a quick review? You're good there? All right. So at some point in the interval 1 to 10, the slope of the secant line is going to equal the slope of the tangent line. Let's find the slope of the secant line first. Matt, what do I have to calculate to get the slope of the secant line? What should I do?
The intended path minus the normal 10, 6 minus 1 over 6 minus 1.
10.5, so it's the difference of the y's over the difference in the x's. So we get 4.5 over 9, which is 1/2. All right, so the slope of the tangent line, slope of the secant line is 1/2. At some point, the slope of the tangent line has to match that. There's going to be some point in that interval where those two things coincide. So we'll see where that happens. Now, as far as f of x is concerned, I don't think I would differentiate it like this. Can anyone suggest a reason why not? Yeah, it kind of almost looks like you need the quotient rule there. So Joshua, suggestions. What could I do to make my life a little easier in differentiating that?
Could you multiply the x?
You couldn't, because that would be changing the function. I can rewrite it. Any suggestions how to rewrite it, Joey?
X plus 5x to negative first.
Perfect. X plus 5x to negative first. That negative just goes with the x. Don't put parentheses around it because you don't want that 5 to be part of the negative. But this should make it a little bit easier to differentiate. So, Gabe, what's the derivative of this going to be, please?
Negative 5 plus 1.
All right, so 1, and then negative 1 times 5 is going to be negative 5. X to what power? When you multiply by the exponent, then what happens to the exponent? You subtract 1, right? So it should be 5x to the negative 2. So at some point, these two things should be equal. Remember, this measures the slope of the tangent line anywhere. That slope should equal 1/2 for at least one point in the interval 1 to 10. So let's see where that happens. 1 minus 5. Let me write it as over x to the second equals 1/2. I'm going to do something I usually don't, which is not mess around to try and avoid a negative. Sometimes it's more work to avoid a negative. In this case, I'm just going to subtract 1 from both sides. And, well, I'm stuck with a negative that I don't really like. So I can divide both sides by negative 1. And that's just going to pleasantly get rid of the negatives for me. 5 over x squared equals 1/2. Suggestions. How would I solve for x? What would you do to solve for x here?
Cross multiply.
Yes. This is a proportion. You have one fraction equals another fraction, so you can cross multiply. I get 10 equals x squared. So plus or minus the square root of 10 equals x. Yay. Plus or minus the square root of 10 equals x. Do I want both of these? Only square root of 10 is in the interval 1 to 10. So really the only answer that works for us is square root of 10. Because that's the only one that's in the interval. Negative square root of 10 might work for, different circumstances. That's fine, but it's not part of our answer here. Comments or thoughts on that one? All right, let's see here. So there's our secant line. It has a slope of 1/2, as you can see right there. Let's throw in our tangent line, which isn't going to be quite as nice and neat and tidy. If you wanted to take a peek at it, there it is. So, not all that great, but the slope of the tangent line does match the slope of the secant line. You got two nice parallel lines here. So, looking good. Okay, a couple more to finish out this section. Let's try example E. Let me shut down example D. And turn on example E. And let's see. We want to restrict this, right? We want to restrict this to the interval 1 to 5. So let's look at just this little piece here. And in particular, we're going to look at the endpoints right here. Now, let's ask ourselves a few questions to try and decide if this is something that satisfies the mean value theorem. What things do I got to check on? Continuous, all right. So Shreya, is it continuous? Is it differentiable? Yeah, it's continuous, differentiable. So we're looking good there. let's see if we can't find slope of the slope of the secant line. Slope of the secant line might not be as warm and fuzzy as some of our previous ones. So x and f of x, 1 and 5. And I'm just going to write ln of 5 here. How about the ln of 1? What is the log of 1? Ooh, check it out on your calculators if you don't know it. Elaine? Log of 1? While you're looking at that, let's take a look at the graph. Log of 1 is 0. Log of any base of 1 is always going to be 0. So let's use this to find the slope of the secant line. And so secant is going to be the log of 5 minus 0 over 5 minus 1, or ln of 5 over 4. Nice. And so tangent. Ashley, I need the slope of the tangent line. How do I find that from ln of x? What's its derivative?
1 over x.
Yeah, 1 over x. So at some point, the slope of the secant line has to equal the slope of the tangent line. And that's what we're going to set equal to each other. So that's going to be 1 over x equals ln of 5 over 4. 1 over x equals ln of 5 over 4. This is another proportion. So we can cross multiply. I get 4 equals x ln of 5. Amber, we're almost done here. What do I need to do to solve for x?
Divide by ln.
Yeah. This is just a number times x, so I'll divide both sides. 4 over ln of 5 equals x. Sweet. That's the point that satisfies the mean value theorem here. And let's see what that looks like on our graph. So here's all our relevant points. And let me just try and make this a little bit more dramatic. There we go. Here's your secant line, and here's your tangent line. Both look remarkably parallel. So looking good on that one. All right, last but not least, example F. So here's your function. It's x minus 3 to the negative second power on the interval 1 to 7. And you're asked to find the value of c that satisfies the mean value theorem. On your mark, get set, go. If you're watching this later, pause the video until you have the answer. Okay, that's enough. You guys are working too hard. Lathe catches it. Does anyone else catch it? Why were you working too hard? Does it satisfy the mean value theorem? No. What's wrong with it? How come it doesn't satisfy the mean value theorem? Yeah, you've got a vertical asymptote here. The function is not continuous, so there's no guarantee that it's going to satisfy the mean value theorem. So, yeah, I'm not going to bother to look. Nice, nice. Do keep in mind the requirements for the mean value theorem to work. There's probably going to be a problem or two that does quiz you or catch you on that stuff. So, comments or thoughts on example F here? All right, let's close the books on the mean value theorem.